Welcome to the world of K-theory. K-theory is a branch of mathematics that uses tools from algebra to study topological spaces. It provides a way to classify vector bundles and explore their connections to both topology and algebra. In essence, K-theory allows us to understand the shape and structure of spaces through the lens of algebraic objects. At the heart of K-theory lies the concept of vector bundles. A vector bundle is a way of assigning a vector space to each point in a topological space, such that this assignment varies continuously across the space. Imagine a surface, and at each point on the surface you attach a vector space like a line or a plane, in a way that smoothly changes as you move from point to point. This collection of vector spaces, along with the original space, forms a vector bundle. This is a key concept. Vector bundles can be combined and manipulated using certain operations, the two most important being the direct sum and the tensor product. The direct sum of two vector bundles combines them by taking the direct sum of their vector spaces at each point. This creates a new vector bundle whose dimension at each point is the sum of the dimensions of the original bundles. The tensor product creates a new bundle by taking the tensor product of the fibers. Let's look at the symbols. Capital E direct sum capital F. Capital E tensor product capital F. Let's consider an example. The tangent bundle of a sphere. For a sphere S superscript 2, the tangent bundle assigns a plane to each point on the sphere, representing the space of all possible directions one could move from that point while staying on the surface of the sphere. Mathematically, the tangent space of the sphere T S squared is equal to the set of ordered pairs x, v, belonging to the sphere S squared cross real number cubed such that x is perpendicular to v. Each tangent plane is a two-dimensional vector space. This is a fundamental way to construct vector bundles from topological spaces. Classifying vector bundles directly can be quite challenging because they are complex mathematical objects. K-theory offers a solution by creating algebraic invariants that capture the essential properties of these bundles. Instead of trying to understand each bundle individually, we group them into equivalence classes based on certain relationships, making the classification problem more manageable. K-theory studies the ring generated by vector bundles modulo stable equivalence. The stable equivalence relation identifies vector bundles that become isomorphic after adding trivial bundles to them. This process leads to the definition of the K-group, denoted as capital K superscript 0 of capital X, which consists of equivalence classes of vector bundles over a space capital X. In simple words, capital K superscript 0 of capital X equals the set of vector bundles over capital X, modulo equivalence. Let's explore some key examples of vector bundles. First, consider a trivial bundle, which is simply a product space with a constant fiber dimension. For example, consider the space capital X cross real numbers to the power of n mapping to capital X. On the other hand, we have the Mobius bundle. This is a non-trivial line bundle over a circle. Topologically, it can be represented as circle S superscript 1 cross real numbers, modulo equivalence. A central result in the theory of vector bundles is the classification theorem. Vector bundles over a space capital X are classified by homotopy classes of maps from capital X to Grassmannian spaces. This theorem provides a powerful tool for understanding the structure of vector bundles by relating them to maps between topological spaces. K-theory finds applications in diverse areas of physics. In string theory, K-theory is used to classify d-branes and Raymonde field strengths in type 2 string theory. In condensed matter physics, K-theory helps classify topological insulators and quantum phases of matter. These applications highlight the power of K-theory to uncover deep connections between mathematics and physics. K-theory continues to evolve and find new connections to other areas of mathematics and physics. Modern frontiers include its relationship to motivic homotopy theory, equivariant topology, and quantum field theories. This vibrant area of research promises to yield new insights into the fundamental structure of space and matter. If you like this video, Hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.